Everyone excited? Yeah. I think I hear a little bit of after effects of the party in everyone. So yeah, thanks for coming. There's a one small quick schedule change. During lunch at 12:30, there'll be a talk from Relayer. They do lots of the little tiny internet devices, Internet of Things, about Scala and that sort of thing. We'll update the schedules out here. That's at 12:30 in here. So if you'd like to see that, get some lunch, come on in. In addition, I'd like to just thank the sponsors of Scala Days and the folks at Trifork. Specifically, is Diana in the house? Yeah, can you stand up? Everyone thank this lady. She has done a phenomenal job. Thank you so much. Everything has been running smoothly. So with that, I'd like to introduce Chad Fowler. I think I saw Chad Fowler speak 2 years ago in Philadelphia, and it was one of the most influential talks to me as a software developer. And it had nothing to do with anything specifically technical. So I'm really excited to have him here today and come and just teach us some very, very insightful pieces of wisdom. So thank you.
Thank you. Hello. Oh, don't clap. Don't clap. It's all right. So he said it was nothing technical. And that's what I'm going to do today, too. The secret is, it's funny, people think that I am a great programmer. Not everyone, but some people think that I'm a great programmer. And most of them think this on the basis of having seen me do talks, etc., none of which are technical. It's really funny. Let's see if this comes on. Yeah. Hello? It was working a minute ago, I promise. Here, I'll unplug it and plug it back in. I'm clearly not very technical if I can't get the slides to work. Is there someone in the house who knows how to make this work? If not, I can speak without it. So once I spoke at this conference called Code Mash in Ohio. Has anyone been to Code Mash? Amazingly, a few people. You're all from the same company, right? Yeah? So Code Mash is in this bizarre resort in Ohio. It's held in the winter when it is freezing cold. And you feel like you're in this 70s Hawaiian resort when you're at Code Mash. And I got up to speak. And as I started, the sound system started making this noise that sounded like that, and it did it for like 5 minutes, and I looked around. You were there, actually, weren't you? You didn't raise your hand. He was there laughing when I was there, when I was trying to do this. Aha, perfect. And I looked at the organizers. This is the bad thing. I looked at the organizers, and I saw their faces, and they were sitting in the audience at the table just going. So finally, I actually went outside and found someone from the hotel during my keynote to fix the problem. Okay, so I know that the keynote is not in presentation mode, so don't worry. It's not going to be one of those embarrassing things where he's like, doesn't he know you can put it in presentation mode? I'm Chad Fowler. I am a systems euthanizer professionally. And by systems euthanizer, I mean I am a person that takes systems that are alive but sick, and I kill them. I kill them. Yeah. It's sad that you're clapping because I'm not happy about it. 7.5 years ago, is it? I wrote this article series that was really popular back then. It was on like dig.com on the front page or something, called The Big Rewrite. And it was about how I was lamenting how I had spent most of my career rewriting software systems, killing them, replacing them with new systems. It's a painful, horrible process. And I was lamenting the fact that I had to do this, because I didn't enjoy these projects. I'm actually in the middle of one of those right now. I'm euthanizing a system. I'm like slowly tearing bits of its heart out until it just bleeds out all over the place. And it really is doing that. In fact, it's doing that so painfully and violently that I was not able to attend the conference until now. And probably I can only attend, oh, this is okay. I can only attend my talk and then I have to leave because I'm in the middle of it. But I hate doing these things, it's sad. The sad thing about it is, as you are euthanizing one of these systems, you are killing someone's work. And in fact, the work that I am now pouring stressfully into every day and night of my life in this kind of crunch time that I'm in, like, it's emotional, you know? You've probably been in these emotional projects where you're just pouring everything you have and you just think it has to work. I have to get it done. We have this huge deadline. It's taxing, right? You might even age in the process, like you're slowly killing yourself as you're killing the system, as you're writing a new system. I realize now, when I'm euthanizing these systems, I'm also destroying, finally, the hopes and the dreams of the developers that built these systems. Like, all the work that you're doing now, that you're working so hard on in your jobs, is probably not going to survive, because someone like me is going to come along and say it sucks and destroy it and throw it away. So I'm a motivational speaker, that's it. Thank you very much. So what happens? You build these things and they become legacy systems. And we have a way that we use the word legacy. It's negative in software, right? Probably when I said legacy systems, you didn't all think, hell yes, legacy systems. You thought, yeah, I've worked on those legacy systems. I have to work on them now. It's terrible. I hate it. Because it means like it's this spin-off, this effect, this thing that you're left with that you don't want, this nasty thing that's hard to change and hard to get rid of that you eventually have to kill, you have to euthanize. But when I'm not a programmer, that's why I don't talk about technical things. I'm a musician that has just been programming longer and paid more when I'm doing programming than music. When I came into software, I remember hearing the word legacy and thinking, oh, that sounds good, because I knew this definition. You leave a legacy. You leave your body of work for future generations to benefit from. Maybe literally your families, maybe the world. You know, I was a composer, and I studied the works of people like Beethoven. Beethoven left such a legacy that even Americans can pronounce his name. But think about it. This, by the way, is Beethoven's 7th symphony. Everyone knows the 9th and the 5th, but this one is the best. So if you don't know it, go listen to it. So he left this body of work. It's still some of the most recognizable music today in today's sad, shallow society where people don't value art. I was also a jazz saxophonist, so you have people like John Coltrane. There's never going to be a sound like that again. Charlie Parker, Ornette Coleman, they have left lasting marks. And not just marks in terms of the fact that both of them have changed the world, changed the way we think of music, but they've actually left the music behind for us. We can continue to enjoy the music. Kurt Vonnegut happens to be one of my favorite authors. Just kind of showing that like authors also have this thing, and we think of ourselves sort of like authors in a way when we're writing. We talk about how we're writing code for other people and not for the machine and all that stuff. Kurt Vonnegut not only has left some of the best fiction behind, he's now unfortunately died a few years ago, but he's changed the way people like me think, because I read his fiction and I hear his words in my head, and it makes me think about the world differently and see the world differently. Architects, this is Gaudi. If you go to Barcelona, the entire city is like a sparse museum for Gaudi. You can go and enjoy his work and be amazed by it. When people stand in front of the cathedral that he built, it's an amazing legacy of work. This one may be a little more controversial, but as you can tell, I'm really into fashion. This is one of the designers from Comme des Garçons, which is a Japanese label. They do a lot of avant-garde stuff, but they create these beautiful things that will always stand the test of time. Pieces of clothing, looks that change the way, they have a ripple effect on the world. So their legacy is actually changing the way people look in the world. Artists, this is Juan Miró. Juan Miró was one of the abstract expressionists. He left an amazing body of work, but also this idea of creating poetry visually in his art. Now, if you didn't know about this, you should look it up. This is actually a poem, a visual poem, and the symbols mean something. It's really fascinating, but it's also beautiful. So much so that I put it on my arm, actually. Yeah, interesting. I didn't realize that. I match. So what does the story look like for us as software developers? This is random, unidentified chunks of the Standish Chaos Report. Are you familiar with the Standish Chaos Report? No? Amazing. So Standish Chaos Report is a kind of survey of the software industry where they measure success, failed, and challenged software projects. And as you can see, the green is successful projects. So it starts in 94 and it skips years and it goes through 2009. You can see there's not really any trend of change. Technology changes, but our ability to create projects does not. The stuff in the middle is the challenged. That means significantly over time or over budget. And then at the top is just failed, scrapped, thrown away. So in my world, where I've been in semi-small businesses, I consider only the green to be good. Everything else means you failed, right? Probably that's true for you too. So we are terrible at actually delivering software as an industry, and probably in this room too, unfortunately. We're just terrible at it. Anecdotally, I would say that the typical piece of business software that we slave over, that we are completely dedicated to creating, has an average life of about 5 years. And I just say that based on my explorations through the world of being a software euthanizer. So 5 years. Well, I don't know if you've seen this one. Joel Spolsky wrote that it takes 10 years to get software right. So congratulations, Scala, it's finally good. Well done, happy birthday. But if most software dies in 5 years, most software is not even launched, as we saw, or it's launched really late and it's considered to be a failure, then we're really in trouble. If it takes 10 years to get it right, that means most software is not right. So this leads to a disturbing realization. As I slave right now, like I'm pouring myself into my work, it's very possible that nothing I do will survive, and no one will remember any of it. So, let's turn the word legacy around. How could we create software that leaves a true legacy? Now, some of us in the room already know how. Scala is going to be around for a long time, and what it has done has left a lasting impact. But most of us don't know how at all. Most of us will not be so lucky unless we really think about it. So that's what I want to talk about. How do we create a legacy of software? So as I was exploring this topic, I went to the expert on legacy code, Mike Feathers. He wrote this book. You should all read it if you haven't, even though it talks about stuff like C++ and Java. It's still valid. And I actually happen to know Mike Feathers. In fact, you can probably see he's wearing a black shirt here. This is the very black shirt that he's wearing in that picture. You're all disturbed because you don't know if I'm joking. I am joking, but I talked to Mike. I talked to Mike on Skype, and I said, Mike, you've been to all these projects, because he wrote this book in like 2003. After he wrote it, he was the only expert in the world on legacy software because he's the only one that wrote a book on it. So therefore, he was consulted with, he consulted many organizations on how to deal with their code. So I said, hey, how do we build legacy software? I explained this idea that I want to build a legacy. And you can see he's thinking really hard, and he's like leaning, and he says, well, I guess you need fear, stasis, and difficulty to change. That's the characteristics of legacy software. So that was pretty disappointing, actually. I said, thanks, Mike, and I hung up on Skype. And I tweeted, software developers, what are the characteristics? Because I wanted this from Mike, and he just said fear, stasis, and difficult to change. What are the characteristics of software systems that survive? Old, still in use software. And as you might guess, I experienced a negative bias, fear of awesome. So like everyone is afraid for something to be good, so they just stick with what they have. That was obviously sarcastic, sunk cost fallacy, old, still in use managers. I like that one. So they kind of missed the point of that tweet, and that's the problem with Twitter. It's too short. But other people got it. They said, it actually adds value, so you don't get rid of it because it adds value, and it works, and it's stable. Like you're afraid to change it, maybe not because it's hard to change, but because why would you change it? I'll tell you some stories of trying to change mainframe software to web-based software and how the web-based software never really made the users happy again. So back, I think, this is 2005. So this is a year before I wrote my big rewrite article, which is actually kind of important timing-wise. My friend David Heinemeier Hansen wrote this post on the 37 Signals /Basecamp weblog, where he was trying to joke about the word enterprise, and he was trying to make everyone feel like the word enterprise was a bad word in software development. And at least in the Ruby world, it now is. Like we bought this. But he said, enterprise is the new legacy, because we all know legacy is a terrible thing to say. So let's start thinking of enterprise that same way. And the first commenter on that post, if you find it, you'll find the first comment says this. I thought it was really insightful. I'm going to read it aloud so you don't have to read it. Careful. Legacy isn't a bad word. Legacy usually means tried, true, and of enough value that it lasted long enough to be old and outdated. To mock legacy is to look at the successes of the past and to declare that they aren't to be revered or respected. Most of what runs our economies is legacy. In the future, I hope the software I'm creating now was highly regarded enough that it's still around and being referred to as legacy. That's a pretty nice aspiration. I thought this was really brilliantly said as I typed it into the comment field. So that was December 2005. And in December 2006, I wrote this thing called The Big Rewrite, which was a big lamenting post about rewriting software systems and how that always fails. Guess what I did in that year? I failed to create something that lasted. And man, I just about killed myself. My wife literally thought I would die. Literally. I don't mean literally like an American, I mean actually. She thought I was going to have a heart attack because I was just, whenever I was awake, which was way too much, I was working on the system and I was so stressed out. And I don't think I enjoyed anything about that year. That was the year I released my second book. I did that somehow while I was working on it, and we did the first RailsConf. We were really busy. Should have been a massively successful, happy year. But to me, it left like a stain on my entire life. And I think back at that project and the people that I worked with, and I feel like maybe some of the only actual regret for anything I've ever done. It's miserable. So, like I said, it's a motivational talk. When I was at GE many years ago, we had this thing called the Honeywell Bull mainframe. Anyone got one of these? No? Okay. So it was a Honeywell Bull mainframe. It was in this room. It was the room, I guess. I'm not sure how you differentiate the room and the computer in this scenario, but it had a custom TCP/IP stack. It had a custom RDBMS. It was like absolutely terrifying. They had been running it for over 20 years when I was there. And they used it for everything. It literally ran the business of GE appliances back then. And we had this team called the Bull Exit Team. The job of the Bull Exit Team is to get off of the Bull because it was this crazy old legacy software. But the Bull Exit Team had been around for longer than I had been a software developer. And when I left, they still had not exited the bull. They'd tried in many ways, and they were not capable. And I think they eventually disbanded the team. So the reason they were trying to get off of this Frankenstein system is, one is it's just scary, and it was all this COBOL stuff, and then of course like assembler that did all the low-level stuff on the mainframe. But the hardware itself was dying, and eventually not replaceable without literally building replacement parts yourself. So we had a team that knew how to replace the bits and pieces of the hardware. Old people here just think, so what? We used to do that all the time, but this was now the late 90s. So amazingly, they had this thing. Now the funny thing about the bull, though, we had a project to get off of it. We kept trying to get off of it. Why could we not? It's not that the projects that we did were bad. It's that the bull was so good, we could not replace it. We couldn't create something that the users would use. We couldn't create something that would perform as well as the bull. So we had this thing, I think it lasted 30 years, ultimately, and it had to be replaced only because of the hardware. So it was a really inspiring thing, although back then I just thought of it as a mess that we wanted to avoid. So how do we create systems that can survive that long? Well, step one, as I talked about in the Standish Chaos Report, you actually have to deliver the system. Probably most of you have used Twitter. If you used it in 2007 or 2008, you saw this picture a lot, and it's been called the fail whale. The fail whale was the subject of a lot of ridicule back then, because the Twitter guys, they built Twitter as a database-backed web application. And if you think about it now, that's just ridiculous, right? A database-backed web application for Twitter. I think it was MySQL, and it was literally just like they typed Rails new Twitter, and it generated the Rails app. And I'm serious. The original engineer who did that lives in Berlin. I bet he's not here right now, but he lives in Berlin. So people made fun of that, and they thought, well, Twitter is a messaging system. It's not a database-backed web application. Well, it wasn't a messaging system until people started using it. When they generated it, it was a database-backed web app. You're just going to put a little message in there, and it's going to show up. It was like a reverse chronological, tiny blogging thing. I think they even called it micro-blogging, which is just silly to think of Twitter as micro-blogging right now. It's not that, right? It's like, it's distributed messaging, and it's literally changing the world. But had they not started with this stupid, idiotic architecture that everyone made fun of, they never would have launched. Like, imagine if in 2007, with two young engineers, they said, let's build a scalable distributed messaging system. Like, one of the engineers I knew because he was my intern at GE, and somehow he ended up at Twitter. He was not capable of building a distributed messaging system at that point. No way. Certainly not a scalable one. He could have built a toy one. So they built it, they launched it, and they were fortunate enough to have built something people wanted to use so much that it crashed. Step one is build it. Step two is get people to crash it because they like it so much. So good job. So Mike did help me with something when I talked to him. We started talking about things that live long. And I was saying, like, I don't take care of myself, and I'm already older than all the software systems that I've ever built. So something about me is going right, and it's not my fault because I eat bad and I don't exercise, I'm terrible. And he was saying, yeah, we think about systems in terms of biology, and he wrote this post called "Your Software is Alive." And in it, he said something kind of negative about old systems, but he says systems survive by providing value, basically, and then being difficult to replace. And I think what he meant to say is when the value is greater than the difficulty, then the system continues to survive. So that's one way to look at it. You need to provide enough value compared to the difficulty of maintaining the thing. And you could even sort of measure yourself and your success that way. Like, got to keep the difficulty low enough so the system is still worth having, that we don't want to kill it. And then he said, the primordial soup is chunky with SQL, ant scripts, and old servlet carcasses. Time goes on and complexity builds. This is not relevant to my talk, but I just thought it was so well said that I just posted on here. So as I continued to explore, I found this really fascinating, it was a talk that was turned into a paper by Dick Gabriel. And Dick Gabriel is one of the first people actually to talk about design patterns in software. He worked on the Common Lisp object system. He's generally just a brilliant guy and probably underappreciated in the mainstream software world. But Dick did this thing called design beyond human abilities. And what he was talking about wasn't making systems that survive forever. He was talking about making systems that were comprised of trillions of lines of code. So like, how would you have to think differently if you had a trillion-line system, which is actually kind of a nonsensical amount of code if you think about how you'd have to generate that. I think you would have to actually combine all the code that's ever been written and then write some more. So what he pulls out, ultimately, is a biological metaphor. And he says biological systems are very much larger than anything coherent that people have built, which is interesting. If you think about all the parts that make up this complex system, me, that has no business continuing to survive, but yet I still stand here and take some of your time, there are a lot of parts to that system, much more than the parts of the system that I'm sweating over at my day job right now. So how do we create systems that can outlast us as biological creatures? Because that's really what I mean. Like if I want to leave a legacy, I kind of mean I have to build systems that are still around after I'm dead. One option is I could just die, but I don't want to do that. So if I want to live quite a long time and the current systems I'm building survive longer, I'm going to think in terms of biology. Now, if you know me, you know that I'm so not a scientist that I have no business talking about this. So I'm going to give you the dumbed-down version. If any of you actually know the real version of this, don't raise your hand. It's not necessary. I know it's wrong, but it's close enough. In biology, there is a concept called homeostasis. And homeostasis is the built-in self-organizing mechanism that organisms have to regulate themselves. So they keep themselves in balance. You know, you have these different competing factions in your body. The brain doesn't typically compete with things, but the brain controls everything. And you have, for example, your liver, which metabolizes toxic substances, and your kidney, which deals with excretion and getting right substances back into your bloodstream, and they sort of compete. They balance each other out. If one fails, the other one will actually be the thing that kills you, perhaps. So if you cannot do this anymore, if you cannot do homeostasis, then you fall into a setting or a mode called homeostatic imbalance. And when you're in the state of homeostatic imbalance, you will probably die. And that's one way people die, like of old age or of kidney failure or liver failure. So homeostatic imbalance means you're going to die. That's okay, because you're dying already. So good news, you're dying right now. Something like 50 trillion cells in your body, 3 million die per second. And this is a guess. It's not my guess. I wouldn't even know where to start. This is a guess that biologists make because they don't know exactly. It's pretty hard to measure. But you always hear this, right? You've heard it since you were a child, that you are physically not the same organism that you were at some point in the past. I don't know how long it takes because I can't do math, and I don't know how many cells you already have and all that sort of stuff. But eventually, you go through life, and toward the end, you are certainly not any part that you used to be, physically, biologically. Interesting. So what are we then? I don't know. It's weird, you know? We're this thing that kind of, we're a cohesive thing that kind of stays together, and it forms a function, and it has a way of being, and we're actually a system. People are each a system. You can replace the components, and the system lives on. And we know in software that if we take this approach and we start thinking about components, like start small with stuff and grow, it's really hard to replace one big massive thing. It's easier to replace tiny things. So when I was asking these questions on Twitter, because that's how I prepare for talks, I said, tell me about the systems that you still use that are old. Like, what are they? And hopefully the ones that you like. And I got a lot of answers that could all be categorized into probably two buckets. One was well-defined systems. So like BSD or Unix, whatever that means, and Emacs. Those are not just applications, those are systems, right? So well-defined systems that have well-defined ways of talking to each other. And then components, small things that do one thing well. For example, grep. Grep's a good one. Everyone uses grep unless they're on Windows, and then they install grep and use it. Or ACK, I guess. I'm so old, I'm sorry. ACK. ACK is what I meant. Not akka, ACK. So we see this in other parts of our lives, like cars. These cars are older than me, and people still drive them down the street. How is that? Imagine if these cars were made of one piece, and the whole thing had to work. If it didn't work, you just had to replace it. They would have all broken the first day, probably, because back then they didn't know how to make things like this, right? But the one thing they knew was that they should have small replaceable components so that the system of the car could continue. And somehow, probably most of the cars that still exist have very few original pieces like in the engines. Although I guess some people care about that and they pride themselves and they collect original pieces from all over the place. But the cars themselves are not the original cars that started, but they effectively are, because the system of the car remains. So if we think about systems like this, then we can probably create something that survives a long time. But we need to ask ourselves, what are the cells in our systems? And what are systems? I think that's one of the core things that we tend to screw up as software developers. And I'll just tell you that based on my anecdotal experience of every project I've ever seen screws that up. Multiple ways, multiple times. And when do you build a system versus a cell? You have a new requirement, what do? Do you build an application? Do you build a component? Are you building the right one now? Are you thinking about the right level of granularity? So I would say that a core thing that I've learned, this is going to be a truism, so I'll finish talking, you'll be like, what? Of course, is small things are easy to deal with. Yeah, small pieces of code, small projects, small people. They're easy to deal with. Small functions, small classes, whatever, small packages. So I would suggest, if we're going to erase things and throw them away and replace them, then we need to think in terms of the smallest component that makes sense. That's what the cell should be. It should be a thing we don't care about destroying and replacing. For my teams, I have a rule which is motivated by something different. I have a rule that says you can build your code in any language you want. Doesn't matter what it is, as long as the code is this big. So I just hold my hands up like this and I say the code must be this big. If it's this big, it can be in Idris or Haskell or anything you want. And it's okay, we'll deploy it. There are a couple of other rules, but this is the main one. Why is that? Because even if it's in Idris, and I've never looked at Idris before, I can look at this much code for 20 minutes maybe with Idris, and by the end of it, I know what this code does. And I can either fix the code, or I can throw it away. If I've never done any Haskell or anything, if it's Idris, I probably have to throw it away, but that's okay. Because it's trivial, and it's understandable, and it's replaceable. So once you have these tiny little pieces that are this big, no more than this big, then you can actually start throwing them away. So I would say that the characteristics of some of the systems I've worked with that have survived the longest, one of the most important characteristics is it's made up of these tiny pieces and they actually were thrown away. Because if you don't start the process of changing things rapidly, then it's going to be really hard the first time you do it. This is something I learned from extreme programming and I have applied to my entire life, which is if something is difficult, just do it all the time, because you're going to then find a way to make it easy. So kill and replace these things regularly. Back to Dick Gabriel. Again, in biology, this happens when a cell is not healthy. An outside cell that's part of the immune system, which is all part of this homeostatic balance thing, can command the cell to destroy itself without spreading any toxins. So that's part of the rules of a system that can survive as long as I can, is that the pieces can be told that they're gone and replaced, and it's okay. And we've actually taken this to another level at Wunderlist, where I work, where we think of our servers as being like cells. They're obviously bigger level cells, but we deploy using a cloud architecture. In this case, it's EC2. We boot up a bunch of systems. We have, they're the smallest systems we can. They have code this big on them. And we throw them away when we're done with them. Now, what does done with them mean? Right now, we throw them away maybe once a day. So systems, there's no uptime. Back in the day, I remember having systems that were up for 2 years, and we were so proud of that. But now I want systems that are not up for a day. Because when something lives for a large amount of time like this, that's a cell, it probably goes bad. We don't know. And one way to force these things to be simple is to force them to go away. Because if you keep replacing them, they keep getting recycled, and you have to think of them that way. So we never upgrade anything on those systems. We only destroy those things, which is a really important rule for us, because when you think of something as a cell, you don't go into the cell and change things. Now again, I'm at a micro level here, or a macro level. I'm talking about Unix systems here, but you could take this down to the code level. You could even have a rule that says every component has a defined interface. If you want to change the component, do not look at the existing code, only throw the component away and rewrite it. That is insane. I saw someone make a face. I'm not saying you should do this, but think about it. So in our world, we're just always changing everything. The system is always a new system. Always be deploying stuff. If you're afraid to change, then you get into this stasis thing and you create the bad kind of legacy software, right? You allow yourself to fall into homeostatic imbalance, and that's when you die. We don't want the system to die. We only want the cells to die. So we have to keep the system changing as soon as possible. I think most of us know that when we create a new software system, if it's a server-based thing, on day 0, we should figure out how to deploy it in an automated way, and then we should start working on it and keep deploying it. So I'm saying do this at a level where all the different bits and pieces are constantly changing and never the same. You get used to it. Now, in order to do these sorts of things, you have to have simple interfaces. So a great example of that has worked very well in the history of software development and software use is Unix pipes. We all know how to use standard in and standard out, and there's just text that goes between them. That's a really nice, simple interface. It's not the only one. Our Bull mainframe, our custom crazy mainframe, we had this thing that we built called Bull RPC. And Bull RPC was just a stupid protocol. We used COBOL copybooks to define the inputs and outputs. So it was kind of like, Corba from the 60s. And I wrote a generator in Ruby back in the year 2000 when Ruby was super cool. I wrote a generator that would create COBOL, Java, Perl, C, etc. Implementations of these COBOL copybooks so that we could do Bull RPC, which means we could trivially port anything to any language, which I'm sure is a huge part of why the Bull survived as long as it did, because it had these simple interfaces that you could work with. And then something new that I have learned from my projects. So my projects, as I say, I'm a software euthanizer, and it used to be that whenever I was going to kill a system, so let's see, I started doing this. I was finally leveled up enough to be the guy who kills software systems in the 90s, and I was taking my Java and I was replacing C, COBOL, etc. I was euthanizing those systems. And then in the mid-2000s, we were all about hacking, killing these Java projects, and in 4 weeks replacing something that took 6 months with a Rails or a Ruby project, Now, of course, we're killing the Ruby projects, and we're replacing it with whatever, Scala. But a very, very common thing that I see in the projects that must be killed is they don't have these simple interfaces. Instead, they've built one big blob, and then they have built really clever abstractions to make that blob scale. So when you're looking at a piece of code in Ruby, If it's just a few lines, it makes a lot of sense. And once you start adding all sorts of things to it, you do crazy tricks, all in memory, in the process space, like hooking into subclasses and monkey patching things and creating this crazy inheritance chain of stuff with modules and mix-ins. And it's terrible. Like, it's a really great way to practice and to be smart as a developer and make things difficult for yourself and for the future and make people impressed with the way you program. But you layer these abstractions, and it ends up being like Java pattern soup. You know, you've all seen the Java projects where it's just so many pattern names and layers of abstraction, you just can't find the thing where the damn database call is made. Just do the database call, generate the SQL as a string, please. So, the new rule to keep these things separate is the components, not only can they be in different languages, they should be. If you don't have a few languages, then you're probably going to allow yourself to be lazy, and you're going to start doing these crazy layers of abstraction. In Ruby, you're going to make a gem that does all kinds of monkey patching and crazy stuff when you need to start scaling your ideas beyond your architecture. In Scala, there's a ton of stuff that you could do. Scala is fun that way too, in the same way Ruby it is. But if you force yourself to have these arbitrary boundaries of technology, of language, it's actually way harder to tightly couple, let's say, C and Scala than it is, obviously, Scala and Scala, right? It's way harder to tightly couple Java and Ruby unless you're using JRuby. But why would you do that? Because you could just use Scala. So you would have to do crazy stuff that would be like a signal to you not to do it, right? But if you're just doing something in one language, you're going to do all this stuff because it's easy. It's the path of least resistance. So we are heterogeneous by default. I said that at Six Wonderkinder, where I work, we have the rule that could be this big. We're running Scala, Ruby, Go, Haskell, Clojure, Node. I can't remember all of them. We're running a bunch of different things in production. And it's working. It's totally fine. Except this week, but it's not the fault of that. The next piece is, since we have to start killing things and replacing things, you want to be dying all the time to survive, as I said, you need to assume that things are going to be failing, right? If you just assume everything is up, then you're afraid to touch it, you're afraid to change it. If you assume that everything is not going to be up all the time, then you can move forward. You can breathe and you can change things and you can relax. So you focus on not mean time between failure, which is the traditional way to think about failure in software or really in systems in general, but more mean time to resolution, and then how you deal with the failure gracefully, right? Because if you're focused on mean time between failure in anything, even in just the way you're delivering projects or the way you're making decisions about your personal finances, you're going to be afraid and you're only going to make big decisions that take a long time. But we want to be in a mode of changing and replacing and evolving all the time. And then instead of worrying about testing all the time, think about monitoring. Because ultimately you don't care if your tests pass if your system still doesn't work or it's down and no one uses it, right? We have like this weird fetish for tests in our industry. I believe TDD is very much alive, speaking of David Heinemeier Hansen, but not because of the tests, just because it's a good way to work. So think about monitoring the stuff you care about, business metrics, for example, system metrics, measure everything. Then you can throw yourself into situations on purpose that are the worst thing that you could feel. So if you're afraid of something, do it all the time. When I joined Six Wonderkinder, the first thing I did, everyone was afraid of the system because they had gone through this massive scaling issue. The first thing I did was I said, well, how many servers are we running for the service right now? And I said, I don't know, 50 or something like that. So I said, okay, let's take it down to 10 and see what happens. And it did this, it crashed. But it was a controlled environment. And when it crashed, we recovered. It was really hard. And they were like, what the hell? Why did we hire this guy? He's an idiot. He's crazy. But we did that a few times, and we did it on a regular basis so that we knew how to deal with it. And we didn't go so far that it ruined the experience for the users. We went so far that it ruined our days. But over time, it doesn't ruin our days anymore, and we've all grown to be able to change things with confidence. So I talked about homeostasis a little bit, and this is sort of the next step for us, because we are building this system of components that are all replaceable all the time. I want to now build the system so that it regulates itself and keeps itself in balance. And I have just a few ways that we've started thinking about how to do this. One of them, this is, I think I just copied this off of the EC2 website. There's not really much information there, but I wanted to show you just a generic application architecture with some boxes and lines on it. This is a system, right? You could think about, if you think about like how your systems work, you're scaling these things, you have databases, you have layers of app servers, you have multiple different services, microservices, whatever they are. Oftentimes what we do when there are issues is the system starts, it gets to be in trouble, and we start looking at all of our logs and graphs, and we find that, oh, it's this component on the bottom left here, it's slowing down for some reason. Why? It's also backing everything else up. So all these guys are in trouble. And what ends up happening actually in a lot of cases is the guy at the top is handling so much load that it's killing the guy at the bottom. So once we now have all these different little bits and pieces, we can start to regulate them on purpose or intentionally, explicitly, and we can say the guy at the top will not continue killing the guy at the bottom because the system will kill the guy at the top. The system will scale up and down. It will throw things away and replace things as it needs to. It starts seeing errors from something, the system just throws that thing away and replaces it with a fresh copy that's exactly like the other one. And weirdly enough, this works. Just replacing systems with themselves or with copies of themselves works, because we're not good at writing, when we're in a hurry and not focused on it, we're not good at writing software that can run for a long time, just run. You know, it builds up, I don't know, memory leaks, or we do stupid things, whatever it happens to be, even if you're not changing it. So the shorter the amount of time the thing lives, the better. Netflix and Pinterest both do two really interesting things with this. Netflix is well known for this thing called Chaos Monkey, which they all have all sorts of chaos star projects now. But when Netflix launched on EC2 originally, EC2 was not really ready for prime time. It wasn't ready for the enterprise. So one of the things that would happen with EC2 is nodes used to die. And it's kind of a myth or an urban legend that they still die, but they don't. I've not seen it. Of course, everything can die. But so what Netflix did is they built this thing that would just simulate killing the nodes as if they had died unexpectedly in production on their live systems. Because they thought, if we're going to work in this environment, it has to always be like this. We just need the normal mode of operation to be that we can't trust the systems to stay up. So let's just make sure they're never staying up. Keep crashing them all over the place. Pinterest has done something really fascinating. Amazon has this thing in EC2 called spot instances. And what spot instances are instances you bid on. So you say, like, I want this many servers of this type, like this amount of workload possible, and I want them to cost no more than this. So you're bidding, right? When the market fluctuates, there's like this whole side market for instances in Amazon. When it fluctuates to where you can afford it, then it will boot those things for you. But then when it fluctuates so you can't afford it anymore, it shuts them down. So I think they created this with the idea that people would just run like offline processing and stuff. You know, you could analyze some log files or whatever. It's a cool idea anyway. But Pinterest said, we're just going to run everything on spot instances. So just randomly, based on fluctuations in the market, for EC2 instances, their servers will be crashed and rebooted. They have like a maximum and minimum, and of course they built in all sorts of stuff so they're not completely dependent on it. But this is really fancy. I'm impressed. In our world, we have not only taken the view of breaking things into separate services, but the services have separate data as well. Because you just have to remove this coupling. You have to keep everything as small as you can, not just the services, also the data. So we are on a quest to keep data tiny. And the first thing was just like all this stuff we thought about relational databases and joins. Most apps don't need it. Most apps don't actually need referential integrity. at least not in the traditional built into the database sense. So we break it apart. Maybe phase 3 of my crazy project, if they let me stay around, is that every Wunderlist user will have their own SQLite file on a hard drive somewhere. And that's how we're going to run it, off of like 10 million, 20 million SQLite files in memory. We want to keep the data as small as possible. Then we'll talk about how to shard the SQLite files. That will be cool. So if you're lucky, you might run into hardware limitations. So you might get to the point where you've built this system and the software can survive, and you're up against this hardware limitation, and the hardware can't survive anymore, and there's no way to port off of it. And I say congratulations if you get to that point. I don't know how to deal with that. I don't care. We don't have this problem, really. We're really lucky if we do. But my hope, my goal for this entire presentation is that none of you again, or at least in the future, at some point in the future, none of you and me, none of us have to go through these big rewrite projects anymore. Because they suck for the many reasons that I have listed in this separate topic. But as I have realized, the main reason they suck is because you are going through and destroying the hard work and effort and energy and passion and love that some other human being or group of human beings has poured into a significant portion of their lives every time you do this. So we need to build systems that can survive so that we don't have to keep on euthanizing them, and we don't have to keep on destroying the work of our colleagues and destroying the legacies of our colleagues intentionally. And that's all I have. Thank you very much.